Every atom in your body is mostly nothing. I mean that literally. But if you took one atom, any atom, and you blew it up to the size of a football stadium, the nucleus would be a marble sitting on the 50-yard line. The electrons would be specks of dust floating somewhere up in the nosebleed seats. And everything in between. Empty. Absolutely, positively, spectacularly empty. So you, sitting there right now, you're made of trillions upon trillions of these atoms, and every single one of them is almost entirely vacant space. By that logic, you should be able to walk straight through a brick wall, the way a swarm of gnats flies through a chain-link fence. The spaces are there, the openings are real, so why can't you do it? That's completely wrong, and I can prove it. See, the picture I just painted for you, the stadium and the marble and the empty seats, that picture is one of the most successful lies in all of physics education. It's not wrong in the way that a fairy tale is wrong. It's wrong in a much more dangerous way. It's wrong because it's almost right. It gets the dimensions correct and the intuition completely backwards. And today I want to show you why. Let me start by making the case for the wrong idea, because it deserves a fair hearing. The people who came up with this picture were not fools. They were brilliant, and their evidence was real. It begins with Ernest Rutherford. Around 1911, Rutherford and two of his students, Hans Geiger and Ernest Marsden, did one of the most beautiful experiments in the history of science. They took thin gold foil, incredibly thin, just a few hundred atoms thick, and they shot alpha particles at it. Alpha particles are little chunks of helium nucleus, 2 protons and 2 neutrons bound together, positively charged, moving at about 5% the speed of light. Fast, heavy for a subatomic particle, little bullets. Now, at the time, the prevailing picture of the atom was J.J. Thomson's plum pudding model. Thomson imagined the atom as a uniform blob of positive charge with electrons scattered through it like raisins in a cake. If that were true, the alpha particles should have pushed through the foil with only slight deflections, like throwing a bowling ball through fog. The positive charge would be spread so thinly that nothing would deflect the alphas by more than a degree or two. And mostly that's exactly what happened. Most of the alpha particles sailed right through the foil as if it wasn't there, right through solid gold. But then something astonishing, about 1 in every 8,000 particles, bounced back. Not slightly deflected, bounced back. Some came back almost the way they'd gone in, reversing direction nearly completely. Rutherford was stunned. He said it was the most incredible event that had ever happened to him in his life. He compared it to firing an artillery shell at a sheet of tissue paper and having it come back and hit you. The only way to explain it was to assume that all the positive charge and virtually all the mass was concentrated in an incredibly tiny region at the center of the atom, a nucleus. The conclusion seemed unavoidable. The atom is almost entirely empty. The nucleus is minuscule compared to the atom's total volume. Do the arithmetic. The nucleus of a typical atom has a radius of about 1 to a few femtometers. That's on the order of 10 to the minus 15 meters. The atom itself, measured out to where the electrons roam, has a radius of about 1 angstrom, which is 10 to the minus 10 meters. That's a factor of roughly 100,000 between the nuclear radius and the atomic radius. And volume goes as the cube of the radius, so the nucleus occupies roughly 1 part in 10 to the 15th of the atom's volume. That's 1 part in 1,000 trillion. The rest empty. Now, really think about what that means. If you could somehow remove all the empty space from the atoms in your body, if you could squish all the nuclei together until they were touching, you would shrink down to something the size of a grain of very fine sand. Everything that makes you you, all 70 or 80 kilograms of bone and muscle and brain, compressed into a speck barely visible to the naked eye. The rest, more than 99.9999999% of your volume, would be gone, because it was never stuff to begin with, and you're made of these atoms. Billions of billions of billions of them. All hollow, all vacant. You should be practically transparent. All right, so that's the argument. And it held up beautifully for a while. Rutherford's model explained scattering data. It explained why matter could be penetrated by certain kinds of radiation. It made sense of the periodic table when Bohr came along and added his orbits. Everything fit together in a nice, tidy package. But there's a problem. Actually, there are several problems, and they get worse the harder you look. The first crack in this picture comes from a question that sounds almost childish but is actually devastating. If atoms are mostly empty space, why is a wall solid at all? Forget walking through it, why doesn't your hand just pass through the table? Why doesn't the chair you're sitting on collapse? Why doesn't the floor give way and send you plummeting to the center of the earth? If you take the empty atom idea seriously, you cannot explain the existence of solid matter. And that should bother you, because obviously solid matter exists. You're experiencing it right now. The answer involves 3 separate pieces of physics, and I want to walk you through each one because they're all doing different jobs. Together they form a fortress, and by the time we're done you'll see that walking through a wall isn't just unlikely, it's forbidden by the deepest rules we know. Let's start with piece number 1, the one that's most familiar, the one people usually mention first when this question comes up. Electromagnetism. Every atom has a nucleus with a positive charge surrounded by electrons with a negative charge. When 2 atoms approach each other, the first things that interact are the outermost electrons, and electrons are negative. Negative repels negative. This is Coulomb's law, one of the oldest and most reliable results in all of physics. 2 negative charges push each other apart, and the force gets stronger the closer they get. It goes as 1 over the distance squared. Halve the distance, quadruple the repulsion. So when your hand presses against the table, what's actually happening at the atomic level is that the electron clouds of the atoms in your hand are getting close to the electron clouds of the atoms in the table, and those clouds are shoving each other away. Hard. The atoms never touch. They never get anywhere close to touching. When we say 2 surfaces are in contact, the atoms in those surfaces are still about 1 to 3 angstroms apart. That's a distance comparable to the diameter of the atoms themselves. At the nuclear scale, they're an astronomical distance apart. What you feel as contact, what you interpret as solidity, is electromagnetic repulsion between electron clouds that still have a comfortable gap between them. Let me give you an analogy that might help. Imagine you're trying to push 2 very powerful magnets together, North Pole to North Pole. You feel that resistance, that springy pushback that gets stronger the harder you shove. Your hand against the table is exactly like that. Except instead of 2 magnets, it's trillions of electron clouds, all pushing against trillions of other electron clouds in perfect coordination. The collective effect is what you perceive as a solid surface. This is already interesting. It means that you've never truly touched anything in your life. Not the hand of someone you love. Not the ground beneath your feet. Every sensation of contact is actually a sensation of electrical repulsion across a gap. Your nerve endings are responding to the electromagnetic force between electron clouds that never quite meet. 2 objects in contact are hovering electromagnetically a tiny distance apart. Always. But is electromagnetic repulsion the whole story? No, not even close. Because here's what it alone doesn't explain. If repulsion between electrons were the only force holding matter apart, you could in principle overcome it. Just push harder, supply enough energy, and you'd squeeze those electron clouds together, force the atoms to overlap, and eventually push through. After all, electric forces can be shielded, they can be overcome. We do it all the time in physics labs when we compress gases, deform metals, even force atomic nuclei close enough to fuse. If it were just electrostatics, there would be some amount of pressure, some amount of force that would let you win. But something strange happens when you actually try to compress atoms. Past a certain point, the resistance doesn't just increase, it skyrockets. It shoots up so fast and so hard that no mechanical force available to a human being, or to a speeding car, or to a freight train can make any further progress. The atoms reach a limit, and they hold, and electromagnetism alone cannot explain that limit. This is the part where things get genuinely weird. And to understand it, we need to throw away the picture of the atom that Rutherford gave us and replace it with something much stranger. Something that, when I first really understood it, made me sit quietly for a while and just think. In Rutherford's picture, and in Bohr's picture after it, the electron is a little particle orbiting the nucleus like a planet around the sun. It has a definite position, a definite speed, a definite orbit. You can point to it on a diagram and say, there it is, going around. And this picture works wonderfully if you're trying to explain the gold foil scattering experiment. But it has a fatal flaw. An electron moving in a circle is accelerating. It's constantly changing direction, and that counts as acceleration. And a charged particle that accelerates radiates electromagnetic energy. That's basic electrodynamics. Maxwell worked it out decades before Rutherford. So an orbiting electron should continuously lose energy by emitting radiation, spiral inward, and smash into the nucleus in about 1/10 billionth of a second. Every atom in the universe should have self-destructed almost immediately after forming. Obviously, atoms are still here. I'm made of them. And you're made of them, so the planetary orbit picture cannot be right. Quantum mechanics came along in the 1920s and demolished that picture entirely. Heisenberg, Schrödinger, Dirac, Born, all these people worked it out piece by piece, and what emerged was nothing anyone expected. The electron is not a little ball. It does not orbit. It does not orbit. It does not have a position until you measure it. Instead, what it has is a wave function, a mathematical object usually written with the Greek letter psi, that tells you the probability of finding the electron at any given location if you were to look. And this wave function doesn't sit in one spot waiting for you. It spreads out. It fills the entire volume of the atom, densest near the nucleus and fading away gradually as you move outward, but never quite reaching zero. In principle, the wave function of the electron in a hydrogen atom extends all the way to the edge of the visible universe. It's negligibly small out there, unimaginably small, but mathematically it's not zero. Now, I want to be very careful here because this is where people's intuition goes haywire. When I say probability cloud, it's tempting to think the electron is really somewhere specific and we just don't know where. Like a pea hidden under one of 3 cups, and the wave function just describes our ignorance about which cup. That's not what quantum mechanics says. That interpretation was explored, and for the standard formalism at least, it doesn't work. The wave function is the complete description of the electron. There is nothing else hiding underneath. The electron genuinely does not have a single location between measurements. It's not that we're ignorant, it's that the question, where exactly is the electron right now, doesn't have an answer until the moment you perform a measurement. Before that, the electron exists in a superposition of being in many places at once, not potentially, actually. So the empty stadium picture is deeply misleading. The stadium isn't empty. It's filled with a kind of quantum presence. The electron isn't a dust speck up in the nosebleeds. It's more like a fog that permeates the whole arena, denser near the center where the nucleus sits, thinning out toward the edges, but genuinely present everywhere within its probability distribution. Think of it this way. If I told you there was a security guard in a building and you wanted to sneak past, you'd want to know which corridor the guard is patrolling so you can go where the guard isn't. But if the guard is a quantum guard, a guard described by a wave function, then the guard is in every hallway, every room, every stairwell, all at the same time. The probability of encountering the guard might be lower in the basement than on the main floor, but it's never zero anywhere inside the building. You cannot find a gap to slip through because there are no gaps. That's what the electron is doing inside an atom. It's everywhere at once. There is no empty lane to walk through. But even that isn't the knockout punch. The knockout punch comes from a principle discovered by a young Austrian named Wolfgang Pauli in 1925, and it's one of the most profound rules in all of physics. A rule so deep that even Pauli himself couldn't explain where it came from. Pauli's exclusion principle says this: no 2 electrons can be in the same quantum state at the same time. Now, what does quantum state mean? It means a complete description of what the electron is doing. In an atom, a quantum state is defined by a set of 4 numbers, 4 quantum numbers. The first one tells you the energy level, basically which shell the electron lives in. The second tells you the shape of its orbital, whether it's spherical or dumbbell-shaped or something more complicated. The third tells you the orientation of that orbital in space. And the fourth tells you the electron spin, which can only be one of 2 values. Think of it as spinning clockwise or counterclockwise, although that's a rough analogy. Pauli's rule says, if one electron already occupies a particular combination of those 4 numbers, no other electron can have that same combination. Each state is a single occupancy room. 1 guest, 1 room, no sharing. If you want to add another electron, it has to go into a different room. This sounds like a minor bookkeeping rule, something you might encounter in an accounting class rather than a physics lecture. But it has staggering consequences. Because of the exclusion principle, electrons in an atom are forced to stack up into different energy levels. They can't all crowd into the lowest, most comfortable state. They have to spread out across higher and higher energy levels, filling up shells the way water fills a cup from the bottom up. And this is what gives atoms their size. If electrons could all pile into the ground state, the lowest energy level, atoms would be tiny, incomprehensibly tiny, but because each electron must occupy a distinct state, the electrons spread out, filling higher energy shells that extend farther from the nucleus, and the atom swells to its actual size. This is also what makes chemistry work. The arrangement of electrons in shells determines how atoms bond to each other, which determines every molecule, every material, every living thing. All from this one rule about not sharing. But here's where it gets relevant to our wall problem. When two atoms come close together, their electron clouds begin to overlap. And when they overlap, the electrons from one atom start to feel the presence of the electrons from the other atom. Pauli's principle kicks in with a vengeance. The electrons from atom A and the electrons from atom B cannot be squeezed into the same quantum states. They refuse. And I want to emphasize how absolute this refusal is. It's not like two people declining to share a seat on a crowded bus, where with enough pushing you could eventually squeeze them in. This is a fundamental law of nature, as rigid and non-negotiable as the law of conservation of energy. No experiment has ever found a violation of the Pauli exclusion principle. Not once. It's as if the universe has a hard rule written into its deepest structure that says identical fermions, which is the class of particles that includes electrons, protons, and neutrons, shall not occupy the same quantum state, not probably won't, not usually don't, shall not, ever. Why? What enforces this? Well, here's where it gets deep. The exclusion principle is really a consequence of the antisymmetry of fermion wave functions. When you write down the wave function for two identical fermions, quantum mechanics demands that swapping the two particles changes the sign of the wave function. Plus becomes minus. And if two fermions were in exactly the same state, then swapping them would change nothing, but the sign must also change, which means the wave function would have to simultaneously equal itself in its own negative. The only number that equals its own negative is 0. So the probability of finding two identical fermions in the same state is 0. Not small. 0. It's built into the mathematics of quantum mechanics as deeply as anything can be. What happens when you try to push atoms together and violate this rule? You have to supply enormous amounts of energy. As you compress two atoms and try to force their electrons into overlapping quantum states, the system screams in protest. The electrons are forced into higher and higher energy levels to avoid doubling up, and promoting electrons to higher energy states requires energy. Lots of it. It's like trying to compress a spring that gets stiffer and stiffer the more you push. Except the spring gets infinitely stiff before you can ever achieve complete overlap. This is called degeneracy pressure, and it's the real reason solid matter holds its shape. Not because atoms are hard little spheres with shells that bump against each other. They're not hard and they don't have shells. Not because electromagnetism alone forbids penetration. It helps, but it's not enough on its own. The ultimate barrier is the Pauli exclusion principle, which says that the quantum states of electrons in overlapping atoms cannot be duplicated, and the enormous energy cost of trying to force them together creates a pressure that resists compression. Freeman Dyson and Andrew Leonard proved this rigorously in 1967. They considered all the forces in play, the attractive forces between electrons and nuclei, the repulsive forces between electrons, the repulsive forces between nuclei, and they showed mathematically that without the Pauli exclusion principle, matter would collapse. Not just get a little smaller, collapse catastrophically. All of it, everything, the attractive forces between negatively charged electrons and positively charged nuclei would win, because attractive forces always win when you don't have exclusion pressure to fight back, and atoms would crumple in on themselves. All the matter in the universe would shrink down to something unimaginably dense. A few years later, Elliott Lieb and Walter Thurring found a simpler proof, same conclusion. Without Pauli, no stability of matter. Let me say that again because I think it's one of the most remarkable facts in physics. The reason you can stand on a floor, the reason buildings stand up, the reason planets have volume and oceans have depth, and your coffee cup doesn't spontaneously compress into a speck, is not because atoms are solid objects that can't overlap. It's because electrons are fermions that obey Pauli's rule, and the energy cost of forcing them into identical quantum states is astronomical. So now let's go back to our wall. What's really between you and the other side? First, there's a wall of electron clouds, all carrying negative charge, all pushing against the electron clouds in your hand. That's electromagnetism. That alone makes it extremely difficult. Second, behind that electrical force, there's Pauli's exclusion principle acting as the enforcer. Even if you could somehow neutralize the electrical repulsion, you'd still face the iron law that your electrons and the wall's electrons cannot occupy the same quantum states. The energy required to force that overlap is not just large, it's beyond anything you could achieve by running at a wall, or hitting it with a car, or hitting it with a train. You'd need pressures comparable to what exists at the center of a white dwarf star. And at that point you wouldn't be walking through anything. You'd be plasma. Let me give you an idea of the numbers involved. The degeneracy pressure in solid matter is already enormous, on the order of billions of pascals. That's what's holding the atoms in a piece of iron apart right now as you look at it. To overcome that pressure and start forcing electron clouds to merge, you'd need to compress matter to densities seen in stellar cores. We're talking about temperatures of millions of degrees and pressures of trillions of atmospheres. That's not walking through a wall, that's nuclear physics. But wait, there's a loophole, or at least it looks like a loophole. And I want to take it seriously because this is where the physics gets delicious. Quantum mechanics has a famous trick called tunneling. And the first time you hear about it, it sounds like exactly the miracle we need. Here's the idea. In classical physics, if a ball doesn't have enough energy to get over a hill, it just rolls back down. Case closed, no way through. But in quantum mechanics, a particle encountering a barrier that it classically shouldn't be able to cross has some probability, some non-zero chance of appearing on the other side of it anyway. The particle doesn't go over the barrier, it doesn't go around it. It doesn't bore a hole through it, it simply has a probability of being found on the far side, as if it ghosted right through. This happens because the wave function of the particle doesn't abruptly stop at the edge of the barrier. It penetrates into the barrier, decaying exponentially as it goes, but not hitting zero. And if the barrier is thin enough, some of that wave function leaks out the other side, which means there's a probability, however small, of finding the particle over there. This is real. This is not philosophy. This is not a thought experiment. This is measured, confirmed, bread-and-butter physics that we use in technology every single day. Alpha particles tunnel out of atomic nuclei, and that's how certain types of radioactive decay work. George Gamow worked out the theory of alpha decay using tunneling in 1928, and his calculations matched the experimental data beautifully. Electrons tunnel through thin insulating gaps between conductors, which is the operating principle of the scanning tunneling microscope, a device that can image individual atoms on a surface. Tunnel diodes, flash memory chips, even certain biological processes like enzyme catalysis all depend on quantum tunneling. So tunneling is everywhere. It's not exotic, it's practical. And the question becomes, can you tunnel through a wall? Can all the atoms in your body spontaneously appear on the other side? Let me be very honest with you, because this is where popular science books tend to get dangerously sloppy. They say something like quantum mechanics tells us there's a tiny but non-zero probability that you could walk through a wall, and then they move on to the next topic, leaving you with the impression that it's theoretically possible, just unlikely, like winning the lottery twice on the same day. It's not like that, not even close. And I want to show you why with actual numbers, because the numbers are where the truth lives. The probability of tunneling depends on three things: the mass of the object doing the tunneling, the width of the barrier, and the height of the barrier, meaning how much energy would you need to get through it by classical means. The formula is beautifully simple. The probability goes as E, that's Euler's number, roughly 2.718, raised to the power of negative 2 times a constant times the square root of the mass times the square root of the barrier height minus the particle's energy times the width of the barrier, all divided by Planck's reduced constant. The critical thing here is that exponential decay is the most brutal function in mathematics. It doesn't taper off gently, it falls off a cliff, and the rate at which it falls depends on the mass. For a single electron, mass about 9.1 times 10 to the minus 31 kilograms, tunneling through a barrier a few atoms wide, say half a nanometer, the probability might be something like 1 in 1,000. Manageable. That's why tunneling microscopes work. For a single proton, which is about 1,836 times heavier than the electron, the probability through the same barrier drops to something absurdly tiny. Not just smaller, exponentially smaller. We're already talking about numbers like 10 to the minus several hundred. For a single atom of, say, carbon with 12 nucleons, The probability is so small that you would need to write a number with thousands of zeros after the decimal point before you hit any digit that isn't zero. Now, you weigh 70 kilograms. That's roughly 10 to the 31st times the mass of an electron. And the exponent in the tunneling probability scales with the square root of the mass. So the exponent for your body is about 10 to the 15th times larger than the exponent for an electron. Plug in reasonable numbers for a wall that's, say, 10 centimeters thick, the kind of wall you'd actually want to walk through, and you get a probability on the order of e to the minus 10 to the 36th power. Let me try to convey how small that is. And it's not just small. It's not just really small. It's a number so close to zero that the distance between it and zero is smaller than any quantity that has ever been relevant to any calculation in the entire history of science. If you tried to write it as a decimal, you'd write a 0, then a decimal point, then 10 to the 36 zeros, and then finally a 1. How many zeros is that? Well, the number of atoms in the observable universe is about 10 to the 80th, so the number of zeros you'd need to write is 10 to the 36th, which is a number so large that you couldn't write down all the zeros. Even if you used every atom in the universe as a writing surface and wrote 1 0 per atom, you'd run out of atoms long before you ran out of zeros. That's not a probability. That's nature's way of saying no, emphatically, completely, and without appeal. And even this absurdly generous calculation is being charitable in at least two ways. First, it treats your body as a single coherent quantum object, which it emphatically is not. Your body is made of something like 10 to the 28th atoms, and every single one of them is constantly interacting with every other one, and with the air molecules bouncing off your skin, and with the electromagnetic field, and with the floor, and with stray photons from the lights above you. All of those interactions cause something called decoherence. Decoherence is what happens when a quantum system gets entangled with its environment, and its delicate quantum coherence gets smeared out and destroyed. For a human body at room temperature, decoherence happens on a time scale of something like 10 to the minus 40 seconds. That's a trillionth of a trillionth of a trillionth of a trillionth of a second. Your quantum wave function doesn't even have time to notice the wall before the environment has already collapsed any tunneling possibility. Second, a naive calculation assumes all your atoms tunnel through simultaneously and arrive on the other side in exactly the same arrangement they started in. But there's no reason they would. Even if by some impossible miracle, all your atoms did independently tunnel through the wall, each one would arrive at a random location on the other side. They wouldn't reassemble into you. They'd be a dispersed cloud of random atoms, which is not walking through a wall. That's being disintegrated by one and reassembled very badly on the other side. So forget tunneling. It's a gorgeous piece of physics, but it offers absolutely no escape route here. Now, I want to mention something that might seem like a contradiction because it's important for the full picture. There are things that pass through walls all the time. Right now, as you sit there, about 100 trillion neutrinos from the sun are passing through your body every single second. They go through you, through the floor, through the entire Earth, and out the other side, and they barely notice any of it. A neutrino is walking through walls. In a sense, yes. But they do it for a completely different reason. Neutrinos don't interact via the electromagnetic force or the strong nuclear force. They only feel gravity and the weak nuclear force, which has an incredibly short range. So neutrinos don't see electron clouds. They don't care about Pauli's principle because they aren't trying to share quantum states with anything. They simply pass through the gaps in the force landscape that are invisible to you and me. For a neutrino, matter is almost perfectly transparent because the forces that make matter opaque to us are forces the neutrino doesn't feel. You, on the other hand, are made of charged particles that interact electromagnetically and are governed by the exclusion principle. You're playing by different rules than the neutrino, and your rules say no passage. Now, some people, clever people, hear all of this and ask a reasonable follow-up question. What about speed? What if you ran at the wall really, really fast? Would that change anything? And I want to take that seriously for a moment because the intuition behind it makes a certain kind of sense. In everyday life, if you throw a ball at a piece of paper, a slow ball bounces off. But throw it hard enough and it rips right through. Speed seems to matter. Force seems to matter. So maybe if you sprinted at a wall at, say, 99% the speed of light, the atoms in your body would have so much kinetic energy that they just punch through the barrier. But this doesn't work, and the reason it doesn't work is instructive. When you throw a ball through paper, What's actually happening is that the ball's kinetic energy is exceeding the binding energy of the cellulose fibers in the paper. You're breaking chemical bonds, you're tearing the material apart. The ball doesn't phase through the paper, it destroys the paper locally and moves through the hole it created. That's not walking through a wall, that's demolition. Could you demolish a brick wall by running at it fast enough? Of course, a cannonball does exactly that, but the cannonball doesn't pass through the wall. It shatters the wall, breaks the atomic bonds that hold the bricks together, and scatters debris in all directions. And the cannonball itself gets deformed and damaged in the process. Both objects are destroyed. Neither one passes through the other intact. The question isn't, can I break a wall? Obviously you can, with enough force. The question is, can I pass through a wall while both the wall and I remain intact? And the answer to that is no, because to pass through the wall without breaking it, your atoms would have to coexist in the same space as the wall's atoms, and that's what the exclusion principle and electromagnetic repulsion forbid. Even at relativistic speeds, the physics doesn't change in your favor. Special relativity tells you that as you accelerate toward the speed of light, your effective mass increases, which means the energy of the collision goes up, which means you'll create a more spectacular explosion when you hit the wall. You won't slip through, you'll make a bigger crater. There's also another quantum mechanical effect working against you that I haven't mentioned yet, and it's subtle but important. It's related to Heisenberg's uncertainty principle. The uncertainty principle says that the more precisely you confine a particle to a small region of space, the more uncertain its momentum becomes. And uncertain momentum means higher kinetic energy. This is not a limitation of our instruments. It's a fundamental feature of quantum mechanics. If you try to squeeze an electron into a smaller and smaller box, its kinetic energy increases. The walls of the box don't physically push on the electron the way the sides of a balloon push on air. Instead, the act of confinement itself, the reduction of the electron's positional uncertainty, automatically increases its energy. This is another reason atoms have the size they do. The electron wants to be close to the nucleus because the electrical attraction is strongest there, but if it gets too close, the confinement energy from the uncertainty principle shoots up and pushes it back out. The actual size of the atom is a balance between these two competing effects. Electromagnetic attraction pulls the electron in. Quantum confinement energy pushes it out. The atom settles at a size where these two are in equilibrium. For hydrogen, that equilibrium radius is about 0.53 angstroms, and we call it the Bohr radius. It's not an orbit, it's a compromise between two quantum forces. When you try to push two atoms together, you're trying to confine their electrons into a smaller volume, and the uncertainty principle raises the kinetic energy of those electrons in protest. This effect works alongside Pauli exclusion and electromagnetic repulsion. It's a third member of the defensive team. You're not fighting one force when you push against a wall. You're fighting at least three distinct quantum and electromagnetisms, all of which get stronger the harder you push. Now let me zoom out for a moment, because I think there's something profound going on that's worth your attention. This whole question, why can't I walk through a wall, is really a question about what solid means, and the answer turns out to be surprising. Solidity is not a fundamental property of matter. There's nothing in the laws of physics that says stuff shall be hard. Hardness, rigidity, impenetrability, these are emergent properties. They emerge from the combination of electromagnetic forces and quantum rules acting on huge numbers of particles. A single atom isn't solid, two atoms aren't solid. But take 10 to the 23rd of them, cram them together under the governance of Pauli's principle and Coulomb's law, and suddenly you have a brick. That's remarkable. The wall is not made of hard things. It's made of rules. The rules say electrons can't share states. The rules say like charges repel. And when you put enough particles together, all obeying those rules simultaneously, the collective effect is a barrier that no force you can exert with your muscles will penetrate. It's a bit like traffic laws. One car on an empty road doesn't produce a traffic jam. But put 10,000 cars on the same highway, all following the same rules about merging and spacing, and you get something that behaves as if there's a physical wall on the road. The wall isn't made of anything extra, it emerges from the rules and the numbers. I want to take this one step further, because there's a beautiful irony buried in all of this. Remember how we started? We said atoms are mostly empty space, and I told you that was misleading. But here's the thing. In one sense it's true, the nucleus really is tiny compared to the atom. There really is no hard little shell around the atom. The electron really is spread out in a cloud. If you had magical eyes that could see at the scale of femtometers, you'd look at a wall and see a sparse lattice of tiny nuclear dots, separated by vast stretches of what looks like nothing, with a faint haze of electron probability everywhere. But looks like nothing and is nothing are very different statements. That faint haze, that probability cloud, is not empty space. It's filled with quantum rules. The emptiness is an illusion created by thinking classically about a quantum world. You look at the distance between the nucleus and the electron cloud and you think gap, but there is no gap. The electron is there. It's there in the way that a wave is everywhere in the ocean, not as a located object, but as a spread-out presence with a definite physical reality. And the exclusion principle means that this presence has teeth. You cannot push through it for the same reason you cannot put two identical fermions in the same state. It's not a matter of force or speed or technique. It's a matter of what the laws of quantum mechanics allow, and those laws say no. Let me tell you about something even more dramatic that illustrates just how powerful Pauli's principle is. And this is one of my favorite stories in all of astrophysics. In the universe, there are objects called white dwarf stars. These are the remnants of dead stars, stars that have burned through all their nuclear fuel and collapsed. A typical white dwarf has about the mass of our Sun, maybe a bit less, crammed into a volume roughly the size of the Earth. The density is staggering. A teaspoon of white dwarf material would weigh about 5 tons here on Earth, and the gravity trying to crush this thing further is immense. There's no nuclear furnace burning at the center anymore, no radiation pressure pushing outward, no thermal energy worth speaking of, at least not on an astronomical scale, yet the star holds its shape, year after year, century after century. What's holding it up? What's holding it up? Electron degeneracy pressure. Pressure. Pauli's exclusion principle, acting on the free electrons inside the star, generates enough outward pressure to counterbalance the gravity of an entire sun's worth of mass. The electrons are being squeezed closer and closer together, forced into higher and higher energy states because the lower states are already full, and the kinetic energy of those high-energy electrons creates a pressure that fights gravity to a standstill. Think about that. The same rule that keeps your hand from passing through a table is the rule that holds up a dead star against the crushing force of its own gravity. The same quantum bookkeeping that says 2 electrons can't share a state in a carbon atom is what prevents a ball of matter 1,000,000 times the mass of the Earth from collapsing into oblivion. That's not a minor principle. That's one of the pillars holding up the visible universe. And it gets more extreme. In neutron stars, where the gravitational pressure is even more crushing, the electrons have been squeezed so hard that they've been forced into the protons, converting them into neutrons through inverse beta decay. And now it's neutron degeneracy pressure, the exclusion principle acting on neutrons instead of electrons, that holds the star up. The density of a neutron star is so extreme that a sugar cube-sized piece of it would weigh about 1,000,000,000 tons. The bulk modulus of neutron star material, which is a measure of how hard it is to compress, is about 20 orders of magnitude greater than diamond. 20 orders of magnitude. Diamond is one of the hardest substances we know, and neutron star material is 100 billion times harder. That's not hard, that's the hardest anything can possibly be, short of forming a black hole, which is what happens when even neutron degeneracy pressure isn't enough. Pauli's principle is the last stand of matter against total gravitational collapse. If you could switch it off, hypothetically, just turn it off for a moment, every white dwarf would implode, every neutron star would collapse further, every atom would shrink, and all the matter in the universe would crumple into states of unimaginable density. The fact that anything has size, that anything takes up space, that your chair holds you and the ground supports you and walls stand upright and stars don't all become black holes, is because of this one quantum rule about identical particles not sharing states. You cannot walk through walls because walls are defended by the same physics that holds up stars. Let me also point out something that I think is easy to miss in all this. The exclusion principle doesn't just explain why matter is impenetrable. It explains why matter exists in recognizable forms at all. Without the exclusion principle, every atom would have all its electrons in the ground state, the lowest energy level. Every atom would look the same. There would be no chemistry, no molecules, no distinction between carbon and iron and gold, no periodic table, no DNA, no life. The entire complexity of the material world, from diamonds to dandelions, exists because the exclusion principle forces electrons to spread out and fill distinct energy levels, giving each element its unique electron configuration and its unique chemical personality. So when you push your hand against a wall and feel resistance, you're not just feeling physics preventing you from going through, you're feeling the same physics that makes you exist in the first place. The wall is impenetrable because of Pauli, but your hand is a hand with bones and skin and nerves also because of Pauli. The barrier and the thing that pushes against it are both products of the same rule. So let me take stock of where we've arrived. We started with a simple, appealing picture. Atoms are empty, therefore matter should be penetrable. We found 3 layers of defense. Layer 1, electromagnetic repulsion between overlapping electron clouds. This is the bouncer at the door. It pushes you away before you even get close. Layer 2, Pauli's exclusion principle and the resulting degeneracy pressure. This is the structural steel behind the bouncer. Even if you could somehow neutralize the electrical repulsion, this quantum law forbids electrons from overlapping in quantum state, and the energy cost of trying is enormous. Layer 3, the failure of quantum tunneling at macroscopic scales. This was the last hope, the idea that maybe quantum mechanics itself provides a loophole. But the loophole closes so dramatically, so exponentially, for anything larger than a subatomic particle that it offers no practical escape whatsoever. Each layer alone might leave a crack. Together they form something absolute, and there's a lesson in all this that goes beyond walls and atoms. The lesson is about the relationship between what you see and what's really going on, about the gap between our intuitions and the actual structure of reality. When you look at a wall, you see a solid, continuous, uniform surface. That's wrong. At the atomic level, it's a lattice of nuclei with electron probability clouds filling the space between them, all humming with quantum activity. When you hear that atoms are mostly empty space, you imagine a sparse, penetrable structure, like a room full of furniture with big gaps between the pieces. That's wrong too. The empty space is saturated with quantum fields and governed by quantum rules that are more impenetrable than any physical substance could ever be. The truth is somewhere that your everyday intuition cannot reach. The truth is that the world is made of mathematics, not matter, not stuff, not hard little balls that can stack on top of each other. Mathematics. The exclusion principle is a mathematical statement about the anti-symmetry of wave functions for identical fermions. Electromagnetic repulsion is a mathematical consequence of charge conservation and the geometry of spacetime. Tunneling probabilities are mathematical consequences of the Schrödinger wave equation applied to potential barriers. Every bit of it is equations, and the equations say you shall not pass, not because the wall is made of something hard, but because the rules are hard. The laws of quantum mechanics and electromagnetism written into the structure of reality itself conspire to create the phenomenon we call solidity. And solidity is not a thing you can point to, it's a consequence. An emergent consequence of rules operating on enormous numbers of particles. A consequence so reliable, so absolute, so backed by the deepest physics we know, that you can lean against a wall with complete confidence that it will hold you up, and that confidence is justified by mathematics that has been tested to more decimal places than any other theory in science. Pauli was once asked about the exclusion principle, whether he could explain why it was true, whether he could derive it from something more fundamental, and he admitted he could not. In his Nobel lecture delivered in 1946, he said he was unable to give a logical reason for the exclusion principle or to deduce it from more general assumptions. He called this a deficiency. He said he had always felt and still felt that this was something missing from our understanding, a rule of immense power, governing everything from the chemistry of elements to the structure of stars, and nobody could explain where it came from. I find that beautiful and a little unsettling. One of the most important rules in all of physics, the rule that gives matter its size and its solidity and its resistance to being walked through. And nobody can tell you why it's true in a deep sense. We can derive it from the spin statistics theorem, which connects the spin of a particle to the symmetry of its wave function. But that just pushes the mystery back one level. Why should spin and statistics be connected? Why should half-integer spin particles have antisymmetric wave functions? At some point you hit bedrock, and the bedrock says this is how the universe is. We discovered it, we tested it to extraordinary precision, we trust it, but the deepest why remains unanswered. Maybe someday someone will figure that out. Maybe some young person listening to this right now, someone who doesn't yet realize they're going to be a physicist, will be the one who cracks it. But until then, the rule holds. It has never been violated in any experiment ever performed. People have looked, they've designed clever experiments specifically to search for even the tiniest violation. Nothing. The exclusion principle is as solid as anything in physics. So, the next time someone tells you that atoms are mostly empty space, and so in principle you could walk through a wall, you can tell them what's actually happening. You can tell them about the electron clouds and Coulomb repulsion and Pauli's principle and degeneracy pressure and the exponential death of tunneling probabilities at macroscopic scales. You can tell them that the empty space inside atoms is the most defended territory in the known universe. And if they still want to try walking through a wall after all that, well, the wall will win. It always does. It has the laws of physics on its side. What I'd like to know from you is this. Which part of this surprises you most? Is it that you've never truly touched anything? That the exclusion principle holds up stars? Or that nobody knows why the exclusion principle is true in the first place? Think about it, and tell me which one keeps you up at night.